Yeah, welcome everyone to our second session of this workshop today. So we now have Professor Anirban Chakraborti from. He is currently the Dean of Research at BMU in Munjal BML Munjal University. He is on a lean there. He was earlier. Professor Chakraborti is a professor at the School of Computational and Integrative Sciences, Jawaharlal Nehru University, New Delhi, where he was a registrar just before he moved to his current position. Earlier, he had worked as an associate professor at the chair of quantitative finance, École Centrale Paris, France, and as a lecturer in theoretical physics, Benares Hindu University. He obtained a PhD in physics from Saha Institute of Nucleophysics, India, and later completed the habilitation in physics from Université Pierre et Marie Curie, France. He has more than 2 decades of experience as a scientist, working in many reputed universities and research institutions in India, Europe, Japan, and USA. He was awarded the prestigious Young Scientist Medal of the Indian National Science Academy in 2009. His main research interests lie in the areas of econophysics, sociophysics, data science, complex systems, statistical physics, quantum physics, and nanomaterial science. So over to you, Professor Chakraborti.
Thank you, Professor Shan Gupta, for inviting me and all the organizers also. And I saw that there's a very nice lineup of speakers, and I'm sure the participants are all enjoying this workshop. Let me share my screen. And is it visible?
Yeah.
Okay, great. So I'll go very slowly, actually, because it's not a conventional topic, and I wanted to present it in an unconventional way as well. So and I titled it "Deciphering Complexity of Financial Networks." And so please feel free to ask me questions, and I have prepared a lot of slides which should give an overview. But if you have more technical questions or things, we can either take it immediately or at the end, as you wish. I would like to thank many of my collaborators, PhD students, master's students with whom I've been working for several years now. And it's a huge list. Many of them I haven't been able to include, actually. These are the ones which are mainly the work that we're going to present today are based on some of the papers that I've been writing with them. And in fact, I think Arijit is also one of your speakers. He'll be speaking tomorrow, so he's also collaborating with us on some aspects. I wanted to tell a little bit about my background so that you understand in what perspective I actually view this whole field of complex systems. And so I wanted to start off with my humble journey from Darjeeling, a very small place in the Himalayas. And I'm sure you can recognize the Mount Kanchenjunga at the background, So every day I used to go past by this capital and go to the school, which was on the other side of the hill, and enjoy this fantastic, spectacle every day. So I studied in St. Joseph's till my class 10th, and then Mount Hermon School for my class 12. After that, I came to Scottish Church College for my bachelor's degree in physics, and then I completed my master's from Calcutta University. And we definitely have that legacy of Calcutta University physics department where person Meghnad Saha, Satyendranath Bose, and other legendary professors were there. And I think it still produces a large number of researchers who are across the Indian institutions, either universities and research institutes. I completed my PhD from Saha Institute of Nucleophysics, and as Shahan already mentioned, that I completed my habilitation, which is equivalent of the DSc from University Pierre et Marie Curie when I was a faculty at École Centrale. For my postdoc, I had spent a little bit more than a year in Helsinki University of Technology, which is now known as Aalto University. And I spent 2 years in Brookhaven National Lab in the Condensed Matter Physics Complex Systems Group. And again, it's very famous for the particle accelerator, the RIC in the background, and we used to have very nice interactions with particle physicists, condensed matter physicists, when we had a chance to be there for 2 years. Then I returned to India as a lecturer in theoretical physics, and I was in BHU. And it's a very nice campus. I don't know how many of you have visited. And it's built in the shape of a rising sun, actually, as you see, and rays of the sun emerging. This is the central office, all the departments and all the hostels, and then the residential areas. And it's like 1,300 acres, this campus. And the other side of Ganga, there's another 2,700 acres. So it's one of the largest in Asia. Then I was offered a permanent position at the École Centrale Paris, and this is taken from my former office. This university was, again, many legendary people like Gustave Eiffel were, alumnus. And all the French car makers that you hear, Citroën, Peugeot, Renault, then the car tire maker, Michelin, they are all ex-students of this École Centrale. And it's been there since 1829 when Napoleon Bonaparte had established all these institutions. So École Normale Supérieure, École Polytechnique, École Centrale, these are among the first few which came up in France. Then 2014, I returned to India as a professor at the School of Computational and Integrative Sciences in JNU. And only in June 2021, I took a long leave from JNU and I joined BML Munjal as the Dean of Research and also as the Dean of School of Engineering and Technology, which is mentored by the Hero Group. And I'm sure if anyone wants to visit, please do get in touch with us and we'll be happy to welcome you. I wanted to spend a little bit about my research, like Sharon mentioned, So in JNU, I used to have a lab which we called etc. because we used to do experimental, theoretical, and computation, ETC lab, actually. I still have my 4 PhD students who are about to finish the PhD. One has just joined, Rishidev, and I think he's among the participants here. And these were my former postdocs and former PhD students who are now working as faculty in different universities. I'm also a founding member of the Center for Complexity Economics, Applied Spirituality and Public Policy in Jindal University. And this we actually started during the pandemic last year. And if somebody would be curious to ask, why applied spirituality, so here is your answer. This is a quote from Das Speth, actually, that, I used to think that top environmental problems were biodiversity loss, ecosystem collapse, and climate change. I thought that 30 years of good science could address these problems. I was wrong. The top environmental problems are selfishness, greed, and apathy. And to deal with these, we need a cultural and spiritual transformation. And we scientists don't know how to do that. So we realize that, when you have to solve problems as complex as these, you have to go beyond these somehow maximization of utility or, there's whatever we learn in traditional economics, nationality, and you have to incorporate, selflessness and altruism and all these things. And this is what we mean by applied spirituality, not that we're giving lessons in religion and spirituality, but, applying these concepts along with the scientific and analytical work that we do. And over the last 1 year, we've been having several panel discussions with, again, leading economists, like Brian Arthur, Dwayne Farmer, Attilio Stella, Stephen Turner. And then we had, again, on quantum social science and public policy, again, a lot of people, and then applied spirituality and public policy. We also had a conference on artificial intelligence in complex socioeconomic systems, and we want to do such events every year. At BMU, I'm mainly focusing my thing on data science, and in fact, I also wanted to announce to you that we're writing a book on complex systems through the lens of data science, and some of my collaborators with whom I'm writing are Untitled Chakraborti from IIM Ahmedabad, Kiran Sharma, who's now joined BMU, Hirdesh Farasi is in Germany, Shubho Bakar is a statistician in Australia, and myself. And this, we would like to get a feedback also. So if you are interested, we can share a few of the chapters with you to get a feedback. So this whole conference is about networks and dynamical systems, and I wanted to present my view of it, from the thing of complexity science. And as you may have seen, that we've been really badly hit by the pandemic over the last 1.5 years. And this was just after the lockdown, was addressed in India last March, and in April, I found an article from BBC where the economists were saying that this was going to be a worst economic crisis since the 1930s depression. And then I came across a very nice article in the month of July last year, written by two professors from Santa Fe Institute, David Kracher and Jeffrey West. Both were former directors of Santa Fe Institute, I think. And they said that the damage we are not attending to. So very nice article written. And this is available in the public domain. So I would request especially the students to go and read that. And they said that scientists who study complex systems offer solutions to the pandemic, and we need to have a different view in order to do this. If you have seen, if you follow, for example, the movements of the Bombay Stock Exchange Index, so this has been given since the 1980s, you'll find that the movements of the market are often related to socio-political events in the country or across the world, And so whenever it was hit, and you'll see that, this is like when Rajiv Gandhi was assassinated, when Manmohan Singh became opened the Indian economy, then Harshad Mehta scam, then the Mumbai blast, again Kargil war. So every event like this actually influences the movements of the markets. And so you realize that, all these things are related in a grander scale, and that's why all these problems become a problem of complex system. It's no longer, in individual parts which you can study in isolation. Because it requires a more holistic picture, and when the pandemic was hit, you see the market going down and dipping, and again it rose back. Now, what was surprising, and this was again a blog written early this year, in February 2021, you would be surprised to find that the Sensex was rapidly rising, and even though the economy was very badly hit, last year we had this severe reverse migration problem with the migrant laborers because they were, homeless, so they were left without their livelihood. In spite of all these economic hits that people have been talking about, the Sensex was doing fantastic well, and it was very counterintuitive. So again, for the students, you might actually try to read and understand why these type of things happen. And so it's very difficult to predict, how the market reacts. Okay? And that's why a large part of it also has been, people have been interested in forecasting based on data. So this I'm pointing out from a paper in 1910, when people were actually looking at the production of corn and its price movement. So this is corn production of the United States and the prices. Another paper like this, published in the American Economic Review was, methods of business forecasting based on fundamental statistics. So people were following the movements, and we were trying to build models which could help in making forecasting. And as of now, you will find that starting from 1930 now, everywhere huge amount of data is available, right? Because across the world now things have become electronic, and large amount of, through the digital transformation, large amount of data is churned out every day. Terabytes of data, actually. Now, what was interesting is that during the conference in January, Diane Farmer presented a slide, which I have borrowed here. And you will see that, these are the 20 years of price changes in the United States in inflation. And you will see that, commodities like television, toys, computer software, wireless telephone, they have all been going down. Whereas essential services like hospital services, college tuition fees, college textbooks, these have steadily increased and increased really rapidly. And then it becomes a matter of concern that, where are we heading as a society, or what policies need to be made. So when we want to actually have effective public policy, we should take into factor all these things, right? And that's why, a huge part or emphasis is being given to this, data-driven science. And so, as you all would know, as students of science, engineering, technology, that we can divide our scientific discoveries in different paradigms. And till the 1650s, right away from the Pythagoras theorem, Euclidean geometry, that was based on empirical observations. And then there was a second paradigm, which was by the invention of calculus and other thing. That took a huge turn towards theoretical modeling and generalizations, and we saw development of electromagnetics, thermodynamics, physical mechanics, quantum mechanics, and all that in physics. And then there came, a paradigm of computation science. So towards the end of the Second World War, when people understood that the importance of computation, churning out again huge amount of data, so we slowly started understanding the importance of computation science. And even, like last 1 or 2 decades ago, people would not, take computational physics so seriously. And people would often, I remember when I was doing PhD, would often criticize the methods. But today they are beginning to appreciate, and I think the community as such is accepting that, computer simulations can be sometimes as effective as what you do in pen and paper or in the lab experiments. Of course, you cannot replace them, but they can have a complementary or approach and give you a lot of insights which are extremely valuable. And then probably from the 2000 onwards, because of the huge advent of cheap computation and large-scale data storage mechanisms, the exploration of data science and AI, ML, all these things have become very important. Now, I wanted to put forward a quotation from Herbert Simon, the Nobel laureate in economics, and he was correct in saying perhaps the right way to move is to understand before one predicts. And so my approach has been like, instead of focusing on prediction and forecasting, my thing was just to data science and machine learning, artificial intelligence, they can very well use to understand the behavior of systems, and especially the subject of complex systems. And I just wanted to give a feature, this is a cartoon which tells, remember the other team is counting on big data. And so based on the previous game, so kick the ball with your other foot. And that's where you have to realize that most of the complex systems that you will encounter in real life are adaptive systems. And so if you have done a strategy which was true 6 months ago in the financial market, may not hold it today. And we have to continuously adapt, do this analytics and then build our strategies. And so you need to understand how this system works. And so that is where you need to bridge the data and the science. And so what we are saying is that this data-driven modeling can be a very, very useful tool. And that's where I think some of the future lies very bright. And I would encourage students to explore these possibilities. Now, traditionally, we've been using, much of the picture has been in science, and the way we do science is like around reductionism. And, I can give an example, very crude one. Like if I ask the question, what are we made up of? Okay, you might say that we're made up of, cells and tissues. So, the skin is a tissue, the bone is a tissue, the blood is a tissue. What are they made up of? Different cells. What are the cells made up of? Again, you have organelles like chromosomes, Golgi bodies, ribosomes, mitochondria. What are these chromosomes made up of? Are they made up of DNA? What is DNA? Deoxyribonucleic acid. What is that made up of? Different chemicals. What are the chemicals made up of? Different atoms. What are the atoms made up of? Electrons, protons, neutrons. What are the protons, neutrons made up of? Quarks. And that's what we do, right? And we've been going into the different domains, starting from probably biology to biochemistry to chemistry to atomic physics to nuclear physics, and then probably to elementary particle physics. Now, this was a wonderful article which was written by Phil W. Anderson in 1972. And he said, the sciences can be arranged roughly, linearly in a hierarchy as particle physics, many-body physics, chemistry, molecular biology, cellular biology, quite the opposite way I described now. But the thing is like this, the elementary entities of one science obeys the laws of the science that precedes it in the above hierarchy, but it does not imply that one science is just an applied version of the science precise. So if I study particle physics, I may not at all understand many particle physics. Or if I'm an expert here, I may not be able to comment anything on chemistry. Or if I am good in chemistry, I may not be able to think. So you will realize that at each stage, entirely new laws, concepts, and generalizations are necessary. Okay, and that's what he was trying to say, that psychology is not simply applied biology, nor is biology applied chemistry. Okay? And therefore, sometimes an integrative approach of complexity is also required. And here again, I wanted to take this scope. This is a very ancient Buddhist parable which existed in ancient India, actually, that if blind men look at the elephant and try to feel out which structures what, they would each blind man might have an idea about the system. So this might touch the trunk and think that it's a snake, touch the earlobe and say that it's a carpet, or the tusk as a sphere. But you need a holistic view. So all of them got together, and they would probably be able to understand that this is an elephant and not what each of them is thinking about. And so in science too, sometimes a holistic approach is required, and that I think the complexity science is playing a very good role. And so again, a very nice edition of articles in the April 99 issue of Science, where they had a lot of articles on complex systems. And you'll find, even to define complexity is very difficult, because each one of us have a different, definition of complex system. But then somehow over the years or decades, we have understood, that there are certain features most of these complex systems have, such as, non-linearity, emergence phenomena, spontaneous ordering, adaptation, feedback loops, and all that, right? And that's why you often need to use tools and techniques from different branches to study complex systems. Again, this is taken from Wikipedia. And in my own research, I have, borrowed things from collective behavior, which is a thing from physics, nonlinear dynamics. Again, most of you are strong experts in game theory, networks, pattern formation. And now I'm all going into, more of artificial intelligence, machine learning, and things like that. So as Shahan had mentioned, I was one of the first PhDs in India on econophysics, and our first few in the world, along with Damien Chalet and some of my former colleagues in France. And, Shita Bruda is also a speaker. I think his talk will start at 7:30. So together we wrote a textbook on econophysics, which is now being used in many universities across the world. We also had edited an econophysics and social physics book. Again, a lot of people, experts from different countries contributed towards these chapters. And you will see contributions coming from different branches in physics and how they are applied to solving problems in economics and finance or in sociology, right? Now, as you had witnessed last decade, that in 2008, we had a big financial crisis. And as such, people could not anticipate, this subprime crisis. So suddenly on September 15th, three of these biggest banks in America, Lehman Brothers, Merrill Lynch, and AIG, failed. And that's why, the economists were sort of taken aback that they could not, even though there were indications that, there's an economic slowdown going to happen or thing, there were a lot of, hustle and bustle about why this happened. And, can we predict or forecast these things? Or can we understand what leads to such crises? And there were a series of articles. One of them was written by a very famous economist, Thomas Lux, and another of his colleague, Frank Westerhoff. So I remember Thomas Lux because I had visited when I was a PhD student, and he had continuously helped me to formulate my problems, because I was from physics background, and his thing was that you have to bring in more economics into your models if you want to be taken seriously in the economics community. But he used to appreciate these facts, and that's what he highlighted in the these boxes, that economic theory offers policymakers little guidance about what to do in the current situation. This is the one which we were talking about in 2008-9 crisis. And then he suggested that economics should take stock of the experience of natural sciences in handling complex systems and strong interactions, right? Because, physicists are typically handling systems which are very strong interaction, strongly correlated electron systems. So I'm sure there's a whole group in IIT Madras, INSC, and other institutes in India who focus on these aspects. Similarly, on complex systems. And there were a series of other articles, again, from Nature and Science. This is from written by Doan Farmer and Duncan Foley, that the economy needs agent-based modeling. And this was a group of, again, physicists, economists, and sociologists writing that economic policy needs interdisciplinary network analysis and behavioral modeling. Now, I won't be able to cover behavioral modeling or agent-based modeling, though a large part of my research, starting from my PhD days, has been on behavioral modeling. And I'll focus mainly on network applications because this is the theme of the current conference. I just wanted to apprise you that, over many years, starting from 2005, we have been holding this conference series on econophysics in India. And from 2010, I have been actively editing books, organizing conferences, and writing. So we have 2 books from Cambridge in last 10 years, one on income and wealth distributions, and the other one on limit order books. And these are part of these proceedings. And you will see that a lot of new concepts were thing. Like after the subprime crisis, people understood that the role of networks is very, very important. And, because we are very strongly connected to other, firms, agents, at the level of countries, at the level of economic sectors, at the level of firms. You cannot measure risk of a person defaulting, as an independent entity. You have to take into account the systemic risk and evaluate the risk from a systemic point of view. And so these are some things which we were focusing in the last few years. I have written 2 back-to-back articles, in review articles in quantitative finance, and these are all another volume of articles which was written by 40 scientists across 30 different countries, summing up the contributions of econophysics. So if you are interested, please drop me an email and I can send you these articles. So coming back to the focus, we all are familiar and been having these talks on networks. So I should not spend too much time. We've applied networks to several social phenomena. For example, starting off, diffusion of languages in space and time. And we upload a thing with my collaborators in France and in Estonia. We've shown, how complex systems tools can be used to studying, for example, the ethno-linguistic developments, right? And similarly, we have tried to apply network analysis to social phenomena like ethnic conflicts, human rights violations, terrorism. Yeah. So if I'm given a spatio-temporal time series, so this shows a map from 1970 till 2017, all the terrorist events that have happened across the globe. And we've just color-coded according to the decade it belonged. And then from this, we have constructed a network, So whenever there's a source which has, attacked or, affected a target, right, we draw a link. And so we can get a directed network. And then you can look at what is the giant component, this is in gray. And from the giant component, then we try to use a different filtering mechanism to understand which are the nodes which are most important, or which are the, edges which are most important. And particularly we have followed, like if you see 70s, Indian subcontinent was very peaceful subcontinent. In 80s, you slowly started having, these extremist movements in certain parts of it. Then in the 90s, it started growing. And today, it's one of the worst affected regions. So top countries are India, Afghanistan, Pakistan, right? And you can see what's going on in Afghanistan now. So we were using these, complex network approaches to studying how the terrorist activities, what patterns were forming, how these things were maturing. Okay, and then you can apply all these rules of, link prediction algorithms, machine learning tools to understand how these may grow in future. And if I have to make public policy, if I have to take counterterrorism measures, what would be the way to do that? Okay, so these are some things which we have been doing. So last few minutes, like approximately 30 minutes, half of the lecture, I'll focus mainly on financial markets, but whatever tools I'm going to show here can be applied to any of these complex systems. And we ourselves have applied, like I showed you, to not only social systems, but also to environmental systems, climate change, and everything else. Okay, so we've had a series of papers in the last 2 decades, and since I was a postdoc in 2002, 2003, and I won't be able to cover much of these, but I'll just tell, we looked at the stock markets where through the co-movements or correlations in prices, we got a network picture. Similarly, you know that each of these stocks belong to a certain sector, so they can belong to IT sector or banking sector, or durable material sector, consumer durables, and different type of sectors. And then each of these sectors also have a price index. So these are called sectoral indices. So even in India, you have in the Bombay Stock Exchange different. So then we have used these network tools to understand that which are the core and which are the periphery. So then it becomes easier for the government to understand. And so this paper was published in Scientific Reports in 2017, which talked about, that how were the sectors hit before, as a result of this 2008 crisis. So how were they behaving before the crisis, and how were they hit or affected? So what was happening after the crisis? And so, these tools can be very effective in that. And if I can cover, I'll cover some of these. And then we've been using whole tools of nonlinear dynamics, random matrix theory, topology thing, so simplicial complexes. I'll try to give a flavor of these, and if you want more details, please feel free to interrupt. But I'll try to show you that, what I was telling, that we have a lot of data. What we need is to understand that how the systems are working. So I want to bridge that data and the science, that's my goal. And using different tools, again, borrowing from random matrix theory, network theory, topological data analysis, persistent homology, everything, I want to understand, for example, how the financial market is working, or how can we use or gain insights about how the markets movements are going on. So market is a very ideal complex system where many agents interact together to find the best price. So this is a collective behavior, right? And that's why physicists are often interested, because we have been modeling collective behavior using statistical physics for very long. So whether you talk about condensed matter theory or in particle physics, statistical mechanics plays a very important role. And so whenever we have a many body or many particle physics, you would have to apply StatMech. Now, the same tools can be applied and adapted to study the behavior of financial market. And because we have huge amount of data coming now, it actually makes life easy, because you can, you have a clean source of data where you can, you can use to model your system. Now, what is interesting is like this. I don't know how many of you have heard about Louis Bachelier, where he was a mathematician who worked under Poincaré and did his PhD. And he worked on the movement of stock prices in the Paris Bourse. And he was the first one to actually derive the theory of Brownian motion, or random walk. And that was 5 years preceding what we know as Albert Einstein's work of Brownian motion. They're slightly different. And if you go and read, it was a few pages article of Louis Bachelier. You can find it from the École Normale website. It's in French. You will see that the textbook derivations we have now is the one which basically is the one outlined by Louis Bachelier. So he was the first one to model the movements of the Paris Stock Exchange bonds as a random walk. Now, physicists have been handling, chaotic time series, which are, deterministic time series. So it could be stochastic like these or deterministic like this. Econometricians and economists were using, these stochastic multiplicative processes, and they call it arch-garch processes to model. But then we find that the financial market is much more complex than any of these systems. And many of the features cannot be modeled using any of these tools or techniques. And so for physicists, it becomes a very interesting and new complex dynamical system, right? And that's why many of the physicists actually have jumped. Don Farmer was one of the early ones who was in Los Alamos and was applying all these chaotic time series to low-dimensional time series and trying to understand. And he, in fact, started a company called Prediction. Then similarly in France, we have Jean-Philippe Bouchot, who has his own company. It's called Capital Fund Management, CFM, and many of my PhD students and master students are working in that company, which is doing fantastic well, actually. And across the globe, I think there are many physicists who have ended up working for banks and ended up in Wall Street jobs. So as I was telling, that it's a very modeled, complex system, and because of this big data, we can actually study, the temporal strong network structure in markets. And that's what we have been focusing. The way we have been doing is, if we are given two time series of the close prices, right? So here, for example, Coca-Cola and McDonald's, yeah. This is a non-stationary time series data. So what I do is I work with the log returns. Yeah, that's what the economics mostly work about. And this makes it sort of a mean stationary process with some variance. And that's why it's truly not a weak stationarity, but it's called a wider sense of a weaker form of stationarity. And then what we can do is, over short time windows, we can compute the correlation coefficients among these prices. Okay. And once I have these correlation coefficients, which all lie between -1 and +1, I can often see how these correlations change. So here I'm taking 194 stocks in the New York Stock Exchange. So there are 194, and I'm just plotting the matrix. So these values are between -1 and +1, because these are the correlation coefficient values, right? So I've arranged these 194 stocks in such a way that all of the similar sector companies are in this. So this is CD, this is CS, this is energy, this is finance, and this is heavy industries, this is IT, and this is utility. So but what is interesting is that you will see that over time windows, as the market evolves, certain times are more peaceful in the sense that they are around this values, right? And in certain times, it's extremely correlated, right? Now, what happens when the market becomes extremely correlated? Now, as you see, these correlation coefficient matrices, correlation matrices evolving, you can look at the PDFs of this correlation. And in certain cases, like I was telling, that there are periods when it is becoming mixed. Now, those are exactly the periods when we have market crash. So the Black Monday, which happened on October 19, 1987, is one of the biggest crashes in. This was the Lehman Brothers. Then there was the Euro debt crisis. Then there was the Greek crisis in 2012. So these are events where you see that the mean correlation goes extremely high. Yeah. And not only that, you will find that, this is the return index, which I'm plotting on top. Okay. This is the mean correlation coefficient. These are the periods when the market becomes very volatile. Okay. And this is the period when, if you evaluate the risk you will take, if I have to invest in the stock market, the risk is extremely high. Okay. So this is something we want to understand. Now, we propose that these are actually sort of the critical states that we encounter in physical systems. And why we say so, that if you look across complex systems, and especially if you have a network picture, you will find certain places where there's a modular structure with a lot of heterogeneity. Okay, and there are other pictures where it is extremely connected with a lot of homogeneity. These are the ones when you have the critical thing. So there was a wonderful article in Science with a group of Sheffer. There are a series of articles there, and we said that that's what we showed in way back in an article where that during a normal market topology there is actually a modularity and heterogeneity, and in a crash all of them actually get more connected and become more homogeneous, in the sense that these colors are actually respecting what is the value of the correlation, which makes it all yellow means they're all similar values. Okay. Now, that's what happens. So in normal market, you have more modular, more heterogeneity. And in the crash times, it becomes more connected and more homogeneous. And then everybody starts behaving in a similar way. Okay. So there are different ways of looking at it and understanding it. So one is through correlation coefficients, and that I was showing. The other one is I can also make a transformation, a nonlinear transformation, where I take this correlation coefficient and convert it into a distance matrix. So if you say -1 +1, you will find that all of them will lie between 0 and 2. So if they are very correlated, the distance is 0. If they are anti-correlated, it becomes 2. Now this definition makes it ultrametric, so it's even better because it is easier to understand the topological features. And so in way back from 2003 till thing, we have been using these features, either minimum spanning tree. So once I convert it into a distance matrix, I can immediately apply the tools of, minimum spanning tree to get a, picture of what is happening in the market. Or I use a tool which is called multidimensional scaling, and it is a very interesting tool in computer science, which tries to project a higher dimensional data into lower, typically 2 or 3 dimension. And so you might have heard of the principal component analysis. So PCA is basically like a multidimensional scaling in 2 dimensions, right? So you take the 2 most principal component, and that's like a multidimensional scaling. So it gives you sort of a map. So if you give the distance matrix as an input, it will give you the coordinates which satisfy the distance matrix. Now, obviously, it's not a unique choice because you can just rotate it or you can translate it and you'll get another set of coordinates because the distance matrix remains invariant under those transformations. However, it gives you a very nice picture of how the thing goes. And I had done a series of articles where I showed, Lehman Brothers, for example, was at the center before the crisis, and it slowly started moving out and became an outlier just before and after the crisis. Yeah, so you can see the market evolution through any of these either network pictures or multidimensional scaling. So I'll show you that corresponding to each of these correlation matrices, I can have these multidimensional scaling maps. So sometimes they will be focused in one, sometimes they'll be clustered, which means that more normal business days, the sectors are working fine. And here they're all working together as if behaving like a single cluster. Yeah, but this is the time when that means the system is becoming critical. Now, when everything becomes, like I told you, homogeneous, that's when you have to be cautious, right? And if I can monitor these, I can devise my strategies when to invest in the market and when not to invest in the market, right? So that's what I'm going to present in the next few slides. So suppose I have these correlation matrices, right? This is 194 cross 194 because those are the stocks that we had in the entire 32-year period that we were studying. We can also look at the distance or similarity between each of these correlation frames. So what we do is a very simple L1 distance, L1 norm distance, which is shown here. Now, if I plot that, immediately you will see that the market, these are the places where the market behaves differently, or these are market outliers. And that's where, the dissimilarity is very high. And these are exactly the periods when we had either crashes or bubbles. So it had the dot-com bubble in the 2000-2002 period, yeah? Lehman Brothers 2008, credit crunch 2010, Euro debt crisis 2012. That's what I was saying. So you can immediately understand that, something goes different during these periods, right? And here, what we can do is if I have all these distances between 1 and 2, 1 and 3, 1 and 4, I can do a multidimensional scaling map in 3 dimensions. So it shows here, actually, we have taken a window of 40 days. And for a 32-year period, we have more than 800 frames. And then I have used the K-means clustering to understand that are there certain patterns which are similar to each other and they occur more frequently than by chance. And you can see that, these are the patterns we identify. So all these magenta ones are the ones which look like this, S4. All these, blue ones are the ones which look like this. All the green ones look like this, and all the black ones look like this. And then what we can say is that, each of these frames correspond to a period of the market, like 40-day period, right? And then because I know which of these frames are, I can go and actually tell when was the market in which state, right? Whether it was in S1, S2, S3, or S4 like this. Yeah, and these S4 are the ones which are the crash states. So if I am given this, I can now compute, what are the frequencies, when are these states and how often are they making these jumps. Yeah, and you can do all these things that we do in StatMech, probability of jumping from one state to the other and like that. And so it also helps you to identify, on a long-term basis that if you are in state 3, you have to be careful because then there's a high probability of going from state 3 to state 4. Okay, so this is one type of thing. The other type I just wanted to talk is, physicists are often interested in phases and phase transitions, right? So you've been studying since your school, for example, the water ice steam system, right? Now, if you ask an experimentalist and a chemist thing, you'll find that the water ice steam system is no longer this simple. It's a much complicated picture, and there are 16 different phases. Okay, and if you want more details, you'll find. So even in the ice phase alone, there are many different phases that you see. Okay, so it's a much complex thing that we were not taught in school, but then when you are doing the research, it is quite evident. And now, can we make a sort of a phase or phase separation, phase transition of the market? And that's what we wanted to do. So, like I showed you that we have this return time series of different stocks. At period, I'm looking at these correlation frames. What we do is, instead of working with the correlation matrix, we take the mod of the element wise and square it so that you satisfy a theorem called the Perron-Frobenius theorem. But once you do that, you can actually calculate the eigenvalues and eigenvectors and the eigenvector corresponding to the maximum eigenvalue. Okay, gives you a picture of what is called the eigenvector centrality in network theory. Okay, so that is what we wanted to see, and there are 194 stocks I told you. And for each of these frames, you will see that there is a strict hierarchy in this, this component of the maximum, the eigenvector corresponding to the maximum eigenvalue. Now, if I have these PIs, which are all lying between 0 and 1, and the summation of these PIs is equal to 1, because these are like probability thing, you can normalize them, then you can write an entropy functional, and you can see how it evolves. So that's what we did. And I was just trying to tell that, eigenvector centrality is one of the measures of centrality, but there are other centralities. So, but we wanted to focus because it is easily understood and linked to the entropy functional. Now, if you know random matrix theory in physics, you will understand that you can always decompose a correlation matrix into different modes. Typically, what we call the market mode, the group mode, and the random mode. So the maximum eigenvalue corresponding to that, you can get this, what is called the market mode. And then there are typically sectors, these deviations from these random matrix part is the one which gives you the sectoral information. So all these eigenvalues, that is what we call the group mode. And the one which is in the bulk, that's called the Marchenko-Pastur distribution, that forms this. So if you have these different matrices in time, which are these correlation matrices, I can always decompose them into CM, CG, CR, or what we did for less arbitrariness, just keep the CM and the CGR, because it's often difficult to distinguish where this CR begins and where the CG begins. So demarcate this. So what we did is for every correlation matrix, then I have a corresponding entropy measure. So from the C, I have a H, from the market mode, I have a HM, and from the CGR mode, I have a HGR. And then I see how that evolves over time. Okay, and that's what we studied in this paper, which was published in the Journal of Physics Complexity. So what you will find interesting is that for that return time series I was showing, I can calculate these mean correlation coefficients, which will tell you when these crashes or bubbles or things are happening. And from the entropy, you can actually identify many of these crises. Okay, and then we found that instead of H, HM, and HGR, there are actually two independent variables. And that if you plot it in a certain thing, you can actually get a phase separation. Very nice events where if we studied for two different markets, one was US and one was Japan, where you will see that all these correlation frames, so each one of these dots correspond to a correlation frame. So all these are market crashes. All these are bubbles. All these are bubble bursts. These are some things which are called anomalies. And these are the periods when we are normal market. Okay. And then we found that, if I look at the mu, which is the mean market correlation, and plot it against H minus HM, they all collapse together. And what is interesting is that this behavior is very similar to what happens in Japan. And in fact, I can show you a video. So this is how the market, evolves over different time. My correlation matrix is changing. And when my correlation matrix changes, I get a different market mode, a different group random mode. And therefore, this hierarchy changes. And you'll see that being reflected. So each one of these dots correspond to a frame, right? And you are moving from one frame to the other. which means you're moving from one place to the other. Now, what may be interesting is that if you pick up a Black Monday crash, so you'll see that this is the one corresponding to the Black Monday crash. For a bubble, it goes in a completely different way. So you can see that, this is where we call the order disorder phase transition in physics, right? So there are order disorder transitions in the market as well. Okay. And what we are now, and this is an ongoing paper which we are writing now, we found the similar behavior not only in the SP 500 New York Stock Exchange or the Nikkei 225 in Japan, but also in London FTSE, Hong Kong SCS, HSCI, Russell 1000. So you'll see a very interesting, sort of a scaling behavior. So we want to understand whether there is a universal behavior in these markets or not, because each of these markets are completely different. However, they share some common properties. Okay. In the last 5 or 10 minutes, I'll just say that once I've built a network, I can do different things. So I'll just skip them because I just wanted to give a flavor that I can also look at what are called discrete curvature measures. This is the work which I've been doing with Arijit, and I don't know if he will cover some of these with. He's been applying it to many domains, especially in biology, chemical metabolism, and other things as well. So we started with the time series, make the correlation matrix, take the distance matrix like so far, and then we compute the discrete curvatures, and we find again, wonderfully, the Foreman-Ritchie curvature, for example, picks up the places where you have bubbles and where you have crashes. And let me tell you, it is not easy to identify the bubbles, and we found that the Foreman-Ritchie curvature does that very well. And that's what we studied, in these respects. And we compared it with all the other topological properties of networks that normally people study. Yeah, and we made these charts and thing. So we found that edges with high negative Foreman-Ritchie curvature are important for maintaining the large-scale connectivity of complex networks, and that's what happens in these things. Yeah. We've also studied different markets across the world and looked at their correlations and movements. Okay, so I won't present them in detail. Again, similar sort of methodology was applied to study how the movements across the globe happens. When do markets become more correlated, when they become more separate? Okay, and again, we have been able to pick up very nice events, how the markets are actually correlated. Now, if that becomes very important, so if I want to invest, in London and I know what is going on in Paris, how do I devise my strategy? Because the London market would open after some time, right? So these time lags can then be used for making what are called arbitration, okay, or it's called making profit from the differences in prices in two different markets. So this is a summary what I was telling. We can also take the same type of distances and use topological studies. Again, I'm very sure in IIT Madras and all the places that you have mathematicians studying very interesting things, which deals with the shape of the objects and so number of pieces and the number of holes, right? And we sometimes joke that a topologist cannot actually see the difference between a coffee mug and a donut, because you can make continuous transformations and change the coffee mug to a donut. Or a topologist doesn't see a difference between a cow and a ball, because with a continuous deformation, you can transform this cow here. Now, the way it's done is that you have these simplicial complexes, which are generalizations of graphs to higher dimensions. So a point would be a zero simplex, a line would be a one simplex, and similarly, you can have higher order simplicials. And you can use what are called the simplicial complexes to understand the homology features. Okay, so homology are typically associated with the topological features, and then you can see with a certain amount of noise. So if you are given a data point, yeah, which are the features that are present or persistent in that actual thing. So you make these changes in the distances, and then you see that actually is a hole present there or not present there. Okay. So this is basically which holes are real and which are noise. So if you are given a whole series of data, you can study the evolution of these homology features H0, H1, H2, and understand what is going on in the data. So what you typically do is, if you have, starting from the the correlation matrices, we had distance matrices. We input them, and then you can convert that matrix state, and you can use the TDA. So when you try to understand, the difference between here and here, you will see, the H0, H1 barcodes different. And so for markets, we have applied the same tools and seen that, corresponding to these 4 correlation matrix states, corresponding to the normal business state, an anomaly, a crash, or a near crash, you'll see the H0, H1 having different structures. Okay. And again, if you look at the L2 norm of that, or, the average H0 or average H1, you will see that they pick up all the signals that are there in the market. So then, you can start understanding the system from different points of view. Okay. And that's what I wanted to present. So this is my Google Scholar page, and you can find all these articles there or from my web page. If you need any article, please feel free to drop me a message. So thank you for your attention. And I think I will have some time for questions. Please shoot your questions, and I'll try to address them. Thank you, everyone, for your patient hearing.
Thanks, Anirban. It was a wonderful talk and very informative. So I see that we have already one person, Ayappa Das. I'll just unmute you. Yeah, you can ask your question.
Yes. Thank you, Professor Anirban. It was indeed a wonderful talk. Before coming to my question, may I just make a comment? There is a
Sure.
there is a statement. It's a very generic one. There is the first line of I believe Anna Karina starts that like all happy families are happy in the same way, and all unhappy families are unhappy, but in very different ways. I think that kind of an inversion of what Tolstoy wrote is what you figured out from the market. I mean, just in a jest.
Okay.
Yeah.
Thank you.
Yeah, sir, my question is basically I have been attempting to use agent-based modeling for some problems. A typical problem, it's not directly connected to financial market, but since you are from econophysics, you should be in a position to at least make a few comments. Let's say Axelrod model for in sociology, like how cultures diffuse, or so and so. Um, how do we make a very decent segregation? I'm not talking about the data part. Data part, well, you might get it from one side or the other. Uh, in your experience, is there any way other than from basic system information to know how to construct those differences, like features and categories or whatever they are? I don't know whether this question is relevant, but since you are a person who has worked in, so I thought I should. Yeah.
Right. So there have been actually several work done in using agent-based model in studying how language, culture, and all spread. We have worked on models on opinion formation, and I can point out these papers to you, and probably I can have a more one-to-one discussion, because I can understand your question is very appropriate, and we've worked a lot on that. But I hope you won't mind if I ask you to connect to me through an email, and then I can address your question.
Sure.
Thank you.
Thank you.
So we have another question in the chat box. It's from Hari Prasad.
Right.
In the phase transition diagram of our water, on the two axes, we have temperature and density. I did not catch what we use for financial markets for the same. Like, what is the analogy of temperature and density for financial markets?
Excellent. So normally that's what you try to do, right? You try to identify, when you're studying phase transition, so that, macroscopic variables which will tell you, this phase separation. So in our case, what we found is something like this, that if I construct that functional H minus HM, H is a entropy function, which I construct from the correlation matrix. If I take the market mode, that will give me an HM. Okay, and the functional, which is H minus HM, that acts as one variable, and the other one is mean market correlation. Okay, so if I take the correlation matrix and I take the average over all the elements, that's mu. Now these two will give you that phase separated behavior. Okay, so those are the two analogies of temperature and density type of things.
Okay, next question is from Subharti. Thank you for such a nice talk. Okay, Anirban, I think you have lost him probably.
No, I can understand. I can hear you.
Okay.
Yeah.
Okay. So Subharti has written, thank you for such a nice talk. Somewhere I read the financial markets share some features of a self-organized criticality and therefore could be the presence of large avalanches which may cause large periods of depressions or events like that. One recommendation was to avoid this. The financial markets would benefit from not operating at an optimal level but in a suboptimal one. Could you please comment on this?
Right. Yeah. So very nice question, and thank you for appreciation. One is, the self-organized feature is present in all markets, and it was actually proposed by Adam Smith, 300 years ago. So the feature of self-organization, and he called it a hand of God. And you will find that hand of God picture in the book of Per Bak, How Nature Works. So Per Bak was the one who proposed the Bak-Tang-Wiesenfeld model, BTW model of sand pile. And then the whole thing of self-organized criticality started in the 80s, right? Now, in the society, in the markets, you would always find, and that concept was proposed by Adam Smith 300 years ago in two of his books. One is called Wealth of Nations. The other one is Theory of Moral Sentiments. And you'll find there, he told that the markets self-organize and the society reacts in such a way that you'll have these cycles, you'll have these periods. So I often tell my students, so now I see a craze in computer science engineering. Yeah, so all the universities, will be teaching that, producing huge number of things. And then what will happen? The number of students in computer science will be very high. The number of jobs will be less. And then again, there will be a cycle. And then this type of cycles you'll see everywhere, not only in education, but all industry sectors. Now in financial market also, we have these cycles. So these are the sectoral cycles I was talking about. What is interesting, and this is different from a physical system, is that, and I often tell, that's why that, I don't try to predict a market crash. Why? Because if I want to predict an earthquake, it's very useful. I would try to evacuate the people so that the damage is less. In financial market, we are part of the system. So if I tell, Shayan, tomorrow we'll have a market crash on, on Monday, what will happen is that he immediately will react, and he will perhaps tomorrow he will try to think, and it will trigger that market crash will be preponed, and it may happen tomorrow. Okay. Now we are part of that system, and so you will see what we were trying to show is that there are certain places where we have that critical thing. Why? Because everybody panics or interacts together. So there's a synchronicity in the market behavior, which leads to perhaps these things. Okay. Now, whether the markets are working at an optimal level or not, it's very difficult to understand, because how people capitalize that information. So that's what we call the efficient market hypothesis. How efficient the markets are, how are they reacting, how the markets react to news or the thing. It's not very well understood. People have an idea that the market is efficient, but it is not totally efficient. So there is a certain amount of inefficiency in the market. And that is what people try to capitalize. Okay, and I think that's why we don't work at the optimal level, and perhaps at a optimal level. So that would be my comment. And whether we can prevent that, going in certain directions or not, very difficult, because it's like I told you, it's a complex adaptive system. So immediately the system adapts, right? And that's what has happened also. People often used to find certain patterns. But if that pattern is known to everybody will try to make use, and that pattern will just, you cannot keep taking advantage of that, anomaly or that pattern you've discovered for very long. Okay. And that's what is actually called the efficient market hypothesis, which was proposed by Eugene Fama, and he was a Nobel Prize winner. He was a student of Mandelbrot, actually. I don't know if you know, Mandelbrot had several contributions in economics, besides in fractal and chaos theory. right? And he was the first one to actually observe what are called the fat tails in the fluctuations of prices. And Eugene Fama wrote a thesis under his thing, developing those theories of efficient market hypothesis. I hope I answered your question partially, if not fully.
Yeah, Subhati, thanks you for such a nice explanation. We have the next question from Gayatri. She has asked, can early warning signals such as lag -1, autocorrelation, skewness used to detect such critical transitions in financial markets?
Very good question. So it depends on actually which scale of data you're looking at, what you want to do. So now the financial markets actually work, tick by tick, what we call millisecond wise. So because of electronic thing and algorithmic trading, you can use the computer to do the trading for you. Okay. Now, at that level, you will find that human beings can't even compute all the data and take the strategies and execute the orders, right? And that's become a problem. So in Europe, regulatory bodies are now saying, should we actually allow individuals to trade stocks where there are big banks and financial institutions as play a role of market makers? Why? Because you won't be able to compete with them. You won't even be able to process all the information and make your strategy and outbid them or beat them, and you'll turn up a loser probably. Okay. Now, if you're trading at that frequency, very difficult to use any of these features. The results that I have been showing were mainly at the daily level, daily returns, and over certain periods you will see these correlation patterns. Now, if you are a slower trader and you're working with these daily prices and you're trying to devise some strategy, then those type of things also help. And people often use, that's called what you call technical analysis. So they use all these things that you are suggesting, including this auto correlations with lagged differences, the market movements, which are the skewness, kurtosis, and everything, and then use it for portfolio optimization, for example. And we've had some papers in the past how to combine these network theories and link it to portfolio. I didn't want to give those applications here, but if you're interested, I can send you those papers actually.
Yeah, so Hari Prasad has a question.
Right.
Say we have methods to identify precursors to identify market crashes. What would be the interventions one would potentially take to avoid such a crash from happening?
That's what I was saying. It's very difficult to make an intervention because as soon as you make an announcement, people will react and it will just prepone the crash. And what happens, and let me clarify this concept. So whenever a crash happens, it's not that everybody loses money. Some people become super rich. What happens is all our money land up in the pockets of a few rich people. Yeah. And so you will see again during the pandemic, initial quarter or 2 quarters, you will see many people, many industries were like having a boom. Why? Because the other sectors were hit. Yeah. And those sectors started, even like online education, edutech companies, health companies, pharma companies, so what happens even in a market is that even in a crash, like I was saying, that if I get that information that there will be a crash tomorrow and I decide not to invest in the market, I will be saving a lot of money. So the market makers, the big banks, players, if they get any information, so they change these strategies. So they understand when to invest in the market and what pieces, the bits and pieces I should invest, where I should invest, and those type of things. And they still make money in these moments of crisis, right? So maybe I am not careful and I lose because I invest in the wrong stocks. I cannot, foresee the risk that I am taking in investing in the stocks. Yeah, I make wrong choices. But there are certainly smart people who are working on those things and they will capitalize on that information they have. So what they do is even if they capture a signal, they don't disclose it because once I disclose it in public, everybody will react. Yeah, but they, in that short time, they will make use of that information and take it in their advantage. And that's what we call, arbitrary arbitrage, statistical arbitrage. Okay.
So
yes, Bijin Joseph. Yeah. In fact, Didier Sonnet had given a talk on these dragon riders in the conference that I organized in January last year. And if you want, I can share his slides at his work. That's right.
So any more questions? No more questions? So then I think if there are no more questions, maybe someone is writing still, I don't know. So if not, then we'll thank Professor Anirban Chakraborti for a really wonderful session. And we hope that we will be able to get you more involved with our center here and yes, and have more talks, more discussions. Thank you very much.
Thank you very much. It was a pleasure.
Thank you. And yes, so with this, we are coming to the closure of this session. We have a 1 hour break, not 1 hour, 50 minutes break, and we will be back with at 7 p.m. with a talk by Professor Sita Brasinha. And then from 8 onwards, we have another talk. That's from 8 to 9, and the speaker is Udit Bhatia from Institute of Gandhi, IIT Gandhinagar. Okay, so we'll just close the session now for 50 minutes, and we'll be back. Thank you, everyone, and thanks, Anirban, once again.
Thank you, Shan. Thank you, Shan. Yeah.
Bye.
Bye.